This lecture is about metal-ligand bonding in an attempt to understand how ligands bond a metal and explain the spectrochemical series. So, a little bit about metal-ligand bonding. When we think about how a ligand binds a metal, we understand that crystal field theory does a good job at predicting the separation of d orbitals in common geometries. From that, we can predict magnetic properties. We can understand things like the ligand field stabilization energy. But the problem is this is not a realistic model of bonding. One of the assumptions of crystal field theory is all bonding is ionic, and we know that in reality that's not true. It also doesn't explain the spectrochemical series. We are able to derive it empirically, but we can't yet explain that. So in order to understand this series and why it works, we have to go to what's known as ligand field theory. And ligand field theory is really an application of molecular orbital theory for these transition metal complexes. And from that, we're going to be able to understand better the bonding in these various complexes. So first, we can summarize how ligands bind to metal, and we can summarize them in three basic types. The first type of symmetry in which a metal can bond a ligand is through what's known as sigma symmetry. And sigma symmetry is almost every ligand possesses this. This is just forming a bond between the ligand and the metal, and this is usually done through a ligand donating an electron pair, like in this case here, where the ammonia is donating its electron pair into an empty d orbital, as shown here, and forming a sigma bond. And so typically we think about this as the HOMO of our ligand going into one of the lower energy unoccupied molecular orbitals of our metal complex. Some examples of ligands with sigma type symmetry include ammonia, this CH3 minus anion, or a hydride. The second type of symmetry we can think about after sigma is what's known as a pi symmetry. And pi symmetries, many ligands contain pi symmetry bonding between the metal. And what's important about these is we need to understand what orbitals are present and which direction this bonding goes in. For example, we can have what we refer to as pi donor ligands. So this is forming a pi type bond, and so the way we'd predict that we can form a pi donor ligand is if the ligand has electrons in something similar to, in this case, what's shown a p orbital, and that p orbital can donate electron density into a metal d orbital. A good example of this, of a type of ligand that can undergo this bonding, is if you have a halide, something like Cl minus, bound to a metal, that's going to be able to donate an electron pair, and that's going to be a pi donor ligand. So really what we're looking for is anytime you have a metal bound to a ligand, and if that ligand has a lone pair on it, there's a good chance that that's going to be a pi donor ligand back to the metal. And then we can also have a pi acceptor ligand. In this case, it's the same type of bond symmetry, but it's the metal that's donating into the ligand. This is also what's known as back bonding, because typically in this situation, the ligand is still donating through a sigma bond, and then what we have is this back donation from a metal d orbital into an empty p symmetry or pi symmetry orbital of the ligand. There's different types of ligands that are able to do this pi accepting. Phosphines have been said to do this through empty d orbitals, and we'll see a little bit later how to recognize some other classes of ligands that can undergo this pi acceptance. So the important thing to take note is when we talked about delta octahedral, we can characterize delta octahedral by whether we have a weak field, which give rise to high spin complexes, and this is a small delta octahedral, Or we can have a strong field, which means you have a large delta octahedral, which is going to result in a low spin complex. Empirically, we developed the spectrochemical series, and we could say things like iodide, bromide, chloride, water would be weak field ligands, so these are going to produce high spin complexes, where things like hydride, cyanide, or carbon monoxide are strong field ligands, which would give rise to low spin complexes. So as you go from left to right on the spectrochemical series, what we're seeing is delta O is increasing. Now, if we look a little further at these ligands, and we can start to classify these various ligands as sigma donating, pi donating, and pi accepting, what we can start to see is that the lower ligands on the spectrochemical series are all pi donor ligands. Things like halides have that lone pair on that atom bound to the metal, which can pi donate. Water is in fact a weak pi donor ligand. Then we have ligands that are sigma donor only ligands, things like EDTA, ammonia, ethylene diamine, and hydride. These are good sigma donors, and the ability of them to sigma donate, the better sigma donor you are, the stronger field ligand you are. And then at the top of the spectrochemical series, what we have is pi accepting ligands. And notice here we have pi accepting ligands are cyanide and carbon monoxide. To understand how these are pi accepting ligands, we have to go back to earlier in the semester when we talked about molecular orbitals of diatomic molecules. And so if we bring up this molecular orbital diagram of carbon monoxide, something we did earlier in the class, right? We took our carbon and oxygen and combined them to form our molecular orbitals. Remember, we said mixing occurs, so if mixing occurs, the pi symmetry orbitals is lower in energy than this sigma orbital, which got raised in energy through the mixing event. And then the key is, when we look at how carbon monoxide binds a metal, we say, well, it's going to donate electron density through the HOMO. So here's our HOMO, and this HOMO is going to undergo sigma donation. And we also know we have a pi star LUMO, and it's this pi star that's going to be able to accept electron density from the metal. So the metal actually back donate into this LUMO of carbon monoxide. And so here's our HOMO, sigma donating from the lobe localized on carbon, and then we can pi accept into the pi star, into the lobe, again localized on the carbon. Right? And so a good rule of thumb, when we think about being able to predict whether something will pi accept, one of the things we're looking for is something, in this case we have our carbon monoxide, which would look like this, and really the key is when you have a multiple bond, a double bond or triple bond adjacent to the metal, this multiple bond will have the pi star LUMO that's available for that metal to bond into. And so when we predict what will be a pi accepting ligand, that's one of the things we're looking for, this multiple bond which will have the pi star LUMO molecule. Now, how does these ligands impact delta octahedral? We still haven't answered the question of why. Why is it a pi accepting ligand has a large delta octahedral? Why does a pi donor ligand have a small delta octahedral? But to answer that, we have to look further into molecular orbital theory and look at the MO diagrams to see how the orbitals move. And for that, we'll go to another lecture, so stay tuned and we can answer that question.